Hello, this is Dr. Maria Weber, and this is your mini lecture about resistance. So let's start first by talking about Ohm's law, which is going to turn out to be a really powerful thing for us. And so we know that the current is proportional to the voltage in our system, and the resistance is defined as being equal to this voltage or potential difference divided by the current. Now, this resistance is measured in units of ohms, represented by a capital Greek letter omega. 1 ohm is equal to 1 volt per ampere. Now, for many materials, resistance remains constant over a wide range of voltages and currents. These materials we call ohmic materials. And with that in mind, we have a relationship called Ohm's law, which is that the voltage is equal to the current times the resistance. And you can also rearrange that to say that the current is equal to the voltage over the resistance. So here we have a schematic of a current. We've got our battery here, or our power source, supplying us with a potential difference. Our current is running from the positive terminal to the negative terminal. It's moving through this resistor. And we can say that the current here is going to be equal to the potential difference, or the voltage from our power source, divided by the resistance of our resistor. Now, the current through an ohmic material is directly proportional to the potential difference. So that was the first equation you saw on the previous slide. Now, this is a graph that represents that same thing. Here we have the current on one axis, and we have the potential difference on the other. And we see that if the current is directly proportional to the potential difference, then we get a straight line here. And the resistance is the slope, or the resistance is 1 over the slope of this line here. So other materials and devices that we call non-ohmic are materials through which the current through the device is not directly proportional to the potential difference. Things that are non-ohmic devices include things like batteries and capacitors. Resistance is a function of the material the electrons in our current are flowing through. And so we have an equation that we can use to find the resistance of a material. And so the resistance is equal to this quantity here, which we call the resistivity of our material, times the length of that material divided by its cross-sectional area. Okay, so here we have some very good conductor, let's say, and it's going to have a resistivity, which is a property of that material. The resistivity has units of ohms times meter, and this resistivity is something that we would have to look up in a chart here. And so I have a chart here of a bunch of different resistivities for a bunch of different metals, things that are good conductors. And so here we're representing this, this conductor, this thing that is a resistor, as sort of like a cylinder where it has some cross-sectional area here and some length. Okay, and so if we look at these conductors here, we see that silver actually has a pretty low resistivity. As we go down here, the resistivity of this material is increasing. So as you go to larger resistivities, that means you're starting to become more and more of a better insulator. So good resistors have low resistivities. Good insulators have high resistivities. Nichrome is a nickel chromium wire that's commonly used in heating elements. We are going to calculate the resistance per unit length, question mark, of a nichrome wire with a radius of 0.321 millimeters. So 0.321 times 10 to the minus 3 meters. Okay, so here's a schematic of my wire. It has some length L, and it has a cross-sectional area. That cross-sectional area, it's the area of the circle. And so that area, the area of a circle, is pi r squared.
To find the resistance per unit length of this wire, we have to go to our equation for resistance. The equation for resistance says that the resistance is equal to rho, but in this case, this rho represents the resistivity of the material. So the resistivity of our nickel chromium wire is 150 times 10 to the minus 8 ohms, not per meter, ohms times meter, okay? That's the unit on resistivity, an ohm times meter. So we have our resistance is equal to our resistivity of the material times the length of the material divided by its cross-sectional area. We're looking for the resistance per unit length, so we just divide both sides by L. If we divide this side by L, we get rid of this L, then we have to divide this side by L. So R over L is equal to the resistivity divided by the area. So the resistance per unit length of this wire is 150 times 10 to the minus 8 ohms times meter divided by the area, cross-sectional area of our wire, which is going to be pi times the radius squared. So 0.321 times 10 to the minus 3 meters squared. And that gives us a resistance per unit length of 4.63 ohms per meter, okay? Because the resistance, we're looking for the resistance per unit length, the resistance over length, that will give us our unit of ohms over meter. Well, this says then that 1 meter of our wire here has a resistance of 4.63 ohms. Okay, that's essentially what this means. The resistance per unit length, 1 meter of our wire is going to have a resistance of 4.63 ohms. Now for part B, if a potential difference of 10 volts is maintained across a 1 meter length of this nichrome wire, what is the current in the wire? So I is equal to question mark. Okay. Well, we can use our equation for Ohm's law. V is equal to IR. If we solve it for I, the current through 1 meter length of this wire will equal to the potential divided by the resistance of a 1 meter length of this wire. And we said that the resistance of 1 meter of this wire is 4.63 ohms. So then the current through my wire is just going to be 10 volts divided by 4.63 ohms. And that gives us a current of 2.2 in the units of currents. The unit of current is the unit of ampere, which we represent as a capital A. Now for part C. The wire is going to be melted down and it's going to be recast with twice its original length. So that means that our, I'm going to call it new length, is equal to twice our original length. Find the new resistance, Rn, as a multiple, equals question mark, of the old resistance, R sub O, or R sub naught, the original resistance. So we're going to figure out what is the new resistance and multiples of our old resistance, the original resistance. To solve this, why don't we go ahead and write down the equation for resistance again. So our new resistance is going to be the resistivity times the new length divided by the new cross-sectional area. Okay? Our old resistance was equal to the resistivity. The resistivity of the material isn't changing. That's a property of the material itself. It doesn't depend on its shape. Times the original length divided by the original cross-sectional area. All right. But let's think about rewriting this equation for our new resistance in terms of the old resistance. Well, this is our resistivity here times the new length is twice the old length, so twice the old length. Now we want to write our new area, cross-sectional area, in terms of our old cross-sectional area. Well, to do that, we need to think about volume. In this wire, we are keeping the same amount of material. We're just changing the length. We're melting it down and reshaping it so that the new length is twice the old length, but we're still keeping the same amount of material that that wire is made up of. So that means that we have the same volume of the material before and after we reshape it. Now volume, since it's going to be the same, the volume of the new wire has to equal the volume of the old wire, or the original wire. A volume of a cylinder, which is essentially what our wire shape is the area, cross-sectional area of that cylinder times length. Okay, so area times length. So that means that our new volume is going to be the new cross-sectional area times the new length, and that has to be the same as our old cross-sectional area times our old length. Okay, and what do we know about, well, let's go ahead and solve this for the new area. We divide both sides by the new length. So the new cross-sectional area is equal to the original cross-sectional area times the original length divided by the new length is twice the old one. So we've got 2 times the old length. We see that the lengths here cancel on top and bottom. So our new cross-sectional area is equal to 1/2 our original cross-sectional area. So we can replace here our new cross-sectional area with our original cross-sectional area divided by 2. Okay, so when we divide by a fraction, that's the same thing as multiplying by the reciprocal. So this turns out to be the resistivity times twice the original length times 2 divided by the original cross-sectional area. So this is equal to our resistivity times, we've got 2 times 2, so that's 4. So actually I'm going to write it like this. Our new resistance is equal to 2 times 2, that's 4. 4 times the resistivity times the original length divided by the original area. So this expression right here, the resistivity times the original length divided by the original area, that's the same thing as our original resistivity. So our new resistivity is 4 times the original. Okay, so we just we reshaped the wire, increased the length by a factor of 2, but we kept the same volume of material. But just by doing that, we actually increase the resistance of the new wire by a factor of 4, just by stretching it out by a factor of 2.
Over a limited temperature range, the resistivity of most metals increases linearly with increasing temperature. So that means that the resistance also changes with temperature. So here's an equation which shows how the resistivity changes with an increase in temperature. And here's an equation which shows how the resistance changes with an increase in temperature. Okay, so rho here is representing our resistivity. The sub O here, or sub 0, that represents our resistivity here, or our resistance here, at some reference temperature. Often this reference temperature is going to be 20 degrees Celsius. The same thing with the temperature here. The temperature is our reference or baseline temperature, T sub O or T sub 0 here. And alpha is called the temperature coefficient of resistivity. and it has a unit of an inverse Celsius. And let's see, so the temperature is here. That would be some final temperature at which the resistor has been warmed to. And the rho here, or the R, that represents the resistivity or the resistance at some higher temperature. Okay, now this chart that I've put in here shows the resistance of a sample of mercury. So mercury here has a 0 resistance, that's on the vertical axis here, at very low temperatures, which is a property of a superconductor. So at low temperatures, mercury behaves like a superconductor. It has no resistance. But above some critical temperature, which is different for each material, its resistance makes a sudden jump and then starts to increase nearly linearly with temperature above this. So at very low temperatures, there are many materials that behave as if they have no resistance, but as they warm up, they start to have a resistance that behaves more linearly.
We're going to apply the temperature dependence of resistance in order to solve this problem. A resistance thermometer, which measures temperature by measuring the change in resistance of a conductor, is made of platinum and has a resistance of 50 ohms at 20 degrees Celsius. Okay, so we've got this thermometer. Inside the thermometer is a piece of platinum. Platinum has here I'm representing as the Greek letter alpha, but that's our temperature coefficient of resistivity. That's this alpha here. That quantity, the temperature coefficient of resistivity for platinum, is 3.93 times 10 to the minus 3 inverse degrees Celsius. So we take that thermometer. The thermometer made of platinum has an initial resistance of 50 ohms at a temperature of 20 degrees Celsius. We're going to dunk that thermometer into a vessel containing melting indium. Indium is the softest metal that is not an alkali metal, just so you know what we're talking about here. So we're going to immerse this resistance thermometer in a vessel containing the melting indium, and then the resistance of the metal, the platinum, inside the resistance thermometer increases to 76.8 ohms. From this information, we want to find the melting point of indium. Okay, so that's going to be the final temperature, essentially, of our thermometer, right? So our thermometer measures temperature by measuring the change in resistivity. This thermometer, we're going to put it into a vat of melting indium. This thermometer is going to quickly match the same temperature as the melting indium. So if we can essentially get the temperature of the thermometer by measuring the change in resistance of the platinum of the thermometer, then we'll also know what the temperature is of the material that it's dunked inside. Okay, so we need to find this final temperature. That'll be the final temperature of our thermometer. It's also going to be the temperature of the melting indium that we inserted the thermometer into. To solve this problem, we're going to use this equation that our final resistance equals our initial resistance times 1 plus alpha times our final temperature minus our initial temperature. Okay, and we need to solve it for this quantity here, our final temperature. So we now really are just doing an algebra problem. Then we need to get rid of this R0 or R0 that's in front of all this term right here. So we divide both sides by this. So R over R0, R0, is equal to 1 plus alpha times T minus T0. Now we need to subtract this 1 over to the other side. So then we have R over R0 minus 1 equals alpha times T minus T0. I'm going to make this look a little bit nicer right here. I'm going to multiply the top and bottom, that's essentially 1 over 1, here, just this one, by R naught over R naught, okay? So this is going to be R over R naught minus R naught over R naught equals alpha times T minus T naught, okay? So we can combine this so that it says R minus R naught over R naught equals alpha times T minus T naught. Now I have to divide both sides by alpha. When I do that, I divide this side by alpha. If I take 1 over alpha here, essentially, I've got R minus R naught divided by alpha R naught, and that equals T minus T naught, okay? Now I just have to add T naught to both sides, or if I add T naught to both sides, now I'm running out of room here. It gets rid of it over here. Add T naught over here. So then we find, I'm going to write this line up here, the final temperature is equal to our initial temperature plus R minus R naught all over R naught. Oh, times my alpha. I've got to put my alpha there too. So our final temperature will be our initial temperature, which was 20 degrees Celsius, plus our, this is our final resistance here, 76.8 ohms, minus our initial resistance, which was 50 ohms, and then we're dividing it by our temperature coefficient of resistivity, which was 3.93 times 10 to the minus 3 inverse degrees Celsius, okay? And then we multiply it by our original temperature, which was 50 ohms, okay? So we've got ohms on top. They cancel with this ohm on the bottom. We've got 1 over an inverse degree Celsius. That'll give us a degree Celsius here. Our answer then is going to be in units of Celsius, so we don't have to worry about, converting these degrees Celsius into Kelvin. And then our final temperature here is going to be 20 degrees Celsius plus this whole term here becomes 136 degrees Celsius. So our final temperature is 156 degrees Celsius. Then in order to solve this problem, we had to think about our equation for the temperature dependence on resistance, and we had to do a little bit of algebra in order to get our final answer.